Next property of solutions we're going to look at is osmotic pressure. Osmotic pressure is a pressure that's caused by the movement of water through a semi-permeable membrane towards a solution that has a solute in it. So this is a semi-permeable membrane. This is something that's of course, very applicable to biology, where our cells are encased in semi-permeable membranes. But for our purposes, they will allow water to go through, but not a solute. So water can go through this semi-permeable membrane. And if we can consider that on the left here, we have a system that has pure solvent here and a solution, meaning we have a solute on the right side. What's going to happen is, because the purple particles there in the solution attract the solvent, some solvent molecules are going to move over. They're going to diffuse into the solution. As a result, we're going to see that the height of the solution is going to increase from what it used to be. And as a result, the side with the solvent will decrease. And as we know, our best friend gravity has its own, things it wants to do, right? Gravity is pulling this down. And so at some point, the water will stop moving through the membrane in a net manner, because gravity can no longer, or the attractive force created by having these new interactions happen can no longer overcome gravity, at which point it stops and you'll now have this difference in heights that you did not have originally. And we're going to see that this causes a pressure. If we were to apply a pressure back onto this, that's a really ugly bracket. Let's fix that. It's still not great. We could apply a pressure to equalize these again, to make it go back to the original state, the state on the left. And we're going to see that that pressure is what's called osmotic pressure. And osmotic pressure actually follows the same pattern as the ideal gas law does. Osmotic pressure, which is capital Pi, because why not, is actually very much related to pressure would be for a gas, right? If you remember, pressure for a gas is nRT over V. Osmotic pressure is the same thing, except we have the Van 't Hoff factor. And if we consider that N over V, moles per liter, is the same thing as molarity, moles per liter, we can rearrange this equation, have it be I, Van 't Hoff factor, times the molarity of the solution, times our gas constant, and the temperature. And now, of course, temperature will have to be in Kelvin, because we're dealing with the ideal gas law again. So our osmotic pressure, which is pi, capital Pi, is the Van 't Hoff factor Van 't Hoff factor, we have the molarity of the solution. We have 0.08206 liter atmosphere per Kelvin mole, our favorite number from Gen Chem 1. And then we, of course, have the temp in Kelvin. So let's go ahead and do some calculations here. Let's see what we can do with the osmotic pressure idea. We're going to see that we can maybe perhaps calculate the osmotic pressure of normal saline. Remember, we use normal saline because it is what's called isotonic with blood. Let's first do some vocabulary. Something that's isotonic, two solutions that are isotonic to each other have the same osmotic pressure. We will also have the words hypertonic and hypotonic, which just relate to one of them being more an osmotic pressure versus the other. You got a higher osmotic pressure if you're hypertonic, and you have a lower osmotic pressure if you are hypotonic. Not you, of course, a solution. So, for example, pure water would have a lower osmotic pressure than salt water. Salt water is hypertonic to pure water. Pure water is hypotonic to salt water. Normal saline is isotonic with blood plasma. Those two have the same osmotic pressure. And so let's calculate what is the osmotic pressure of normal saline, 0.090%, at body temperature. So we're going to effectively calculate the osmotic pressure of blood. So what we need here, we need a Van't Hoff factor, we need a molarity, we need a gas constant, which we already have, and then we need the temperature in Kelvin. So we have, let's go ahead and copy our equation. The osmotic pressure is I times the molarity times our R, our universal gas constant, and the temperature. So for this one, I should be 2, because it's sodium chloride. The molarity we'll calculate in a sec. R we've got. The temperature is going to be 310 Kelvin. If we want to find the molarity, well, this is a great time to review our converting in between solution concentrations. We're going to go ahead and assume, I should probably have said this before, we're going to assume a density of 1.00 grams per mil. We're going to assume that our salt water has the same density as pure water, and that's pretty close, 0.9%, not very much, right? So 0.9% is the same thing as saying we have 9 grams, we could say 0.9 grams, in 100 grams of solution, right? 0.9%. So 0.9 per 100. That's what percent means, right? Per cent. Century, 100. So this would be of solution, and that's of sodium chloride. The proportion is the same for 9 grams over 1,000 grams solution. If we're assuming a density of 1, that means it's 9 grams, or 9.0, we should be good with our sig figs, per liter of solution. And so now it's simply a matter of getting from that 9 grams to moles, and then we'll have our molarity. So with this, we can go ahead and multiply by our molar mass, or rather divide by it, 58.44. Is that right? Yeah, 44. So 9 divided by 58.44 is 0.154004 molar, right? Grams per liter. We've converted to moles per liter, which is molar. We have 2 sig figs here. Now we can plug all this stuff into our equation. So pi, osmotic pressure, is 2 times 0.154 molar. And I'm going to actually put out the units so we can see how they all cancel out. We have 0.08206 liter, atmosphere, mole, Kelvin, and 310 Kelvin. That's all the stuff from our equation, IMRT. Let's check our units that are going to cancel out so we can see what the unit of our final answer will be in. Moles cancels, Kelvin cancels. We're left with atmospheres, which is a unit of pressure, right? And so that makes sense for us. All right, and then doing all this, we're going to have to crunch the numbers. So 2 times 0.154 times 0.08206 times 310, and we get 7.8. Looks like we only have 2 sig figs, so 7.8 atmospheres. So that's the osmotic pressure of our blood, or for normal saline, which is supposed to be isotonic with blood. So we're going to see that we can use all of these colligative properties we've talked about to calculate things. They're very useful in analytical chemistry, particularly for calculating the molar mass of an unknown substance. And so we'll see that's their biggest utility. So we can use osmotic pressure, we can use boiling point or freezing point, or we can use vapor pressure. Any of these four will allow us to experimentally determine the molar mass of an unknown compound. And we'll see that in the next video.